Case study: Revolutionizing Cybersecurity, AI-driven proactive vulnerability management in diverse network infrastructures. AI-driven vulnerability management models are revolutionizing cybersecurity by integrating advanced techniques to predict, identify, and mitigate potential threats. In an Office of Cybertech Solutions, a cybersecurity firm specializing in vulnerability management, the team faces the daunting challenge of protecting an extensive and diverse network infrastructure. The company's Chief Information Security Officer, Sarah, is keen on adopting AI-driven models to enhance their security posture. Sarah's team is composed of seasoned security analysts like John, who has spent years in traditional vulnerability management, and new recruits like Emily, a data scientist with a background in machine learning. Together, they embark on a journey to integrate AI into their existing security framework, aiming to transition from reactive to proactive vulnerability management. One of Sarah's primary concerns is how to effectively handle the vast amounts of data generated by their network. With logs, network traffic, and system configurations accumulating exponentially, the human analysts are overwhelmed. Sarah questions whether AI models, particularly those based on deep learning, can manage this data influx and uncover hidden patterns that might be overlooked by human analysts. Emily explains that convolutional neural networks, traditionally used in image recognition, can be adapted to analyze network traffic data, potentially identifying anomalies that could indicate vulnerabilities. This adaptability of CNNs to cybersecurity tasks is a promising solution to the data overload problem. The team faces the challenge of ensuring the quality and diversity of their training data. They understand that the efficacy of AI-driven models largely depends on the richness of the datasets used. Emily suggests leveraging transfer learning, where a model trained on detecting vulnerabilities in one context, such as web applications, can be fine-tuned to work with different data, like mobile applications. Sarah wonders how well this technique will perform in their varied network environments. To address this, they decide to compile a comprehensive dataset that includes a wide range of vulnerabilities from different systems and applications. Another crucial aspect of their strategy is natural language processing. Sarah realizes that analyzing textual data, such as vulnerability descriptions, security advisories, and threat intelligence reports, can provide valuable insights. John raises a concern about the capability of NLP techniques to process and analyze unstructured text effectively. Emily reassures him by highlighting techniques like named entity recognition and sentiment analysis that can extract relevant information from unstructured text, enabling automated processing and analysis. Implementing these NLP techniques can keep the team updated with the constantly evolving threat landscape, allowing for timely and accurate vulnerability management. The team also explores the potential of reinforcement learning in developing automated patch management systems. Sarah is intrigued by the idea of RL models learning optimal strategies through trial and error, but she questions how RL can prioritize and apply patches based on their criticality and potential impact. Emily explains that RL models receive feedback from the environment in the form of rewards or penalties, which helps them to continuously improve their decision-making processes. This capability ensures that the most critical vulnerabilities are addressed promptly, enhancing the overall security posture of the organization. One of the most significant concerns for Sarah is the explainability and transparency of AI models. She is aware that while AI models, particularly deep learning ones, can achieve high levels of accuracy, their decision-making processes are often opaque. John is skeptical about trusting AI models without understanding how they arrive at their conclusions. Emily introduces techniques from explainable AI, like LIME, which can provide insights into which features contributed to a model's prediction. This transparency can help security analysts like John understand and trust the AI's recommendations, bridging the gap between AI and human expertise. The team also emphasizes the importance of robust evaluation and validation processes for their AI models. Sarah insists on using metrics such as precision, recall, and F1 score to assess the model's performance. Emily suggests employing cross-validation techniques where the dataset is partitioned into training and testing subsets to evaluate the model's generalizability. Continuous monitoring and updating of the models are necessary to maintain their effectiveness in the face of evolving threats, ensuring that the models remain accurate and reliable over time. As the team progresses, they recognize that the adoption of AI-driven vulnerability management has broader implications for their cybersecurity strategy. Moving from a reactive to a proactive security posture can lead to substantial cost savings by reducing the resources required for incident response and minimizing potential damages from cyber attacks. John notes that AI models can augment the capabilities of security teams, allowing them to focus on more strategic tasks rather than being overwhelmed by routine vulnerability assessments. This shift not only enhances their operational efficiency, but also strengthens their overall security framework. However, Sarah is mindful of the challenges and ethical considerations associated with integrating AI into vulnerability management. She is particularly concerned about the potential for adversarial attacks, where attackers manipulate input data to deceive AI models. Emily explains that developing robust AI models that can withstand such attacks and implementing complementary security measures to detect and mitigate them are crucial. This dual approach can help safeguard the AI models from being exploited by malicious actors. Ethical considerations also play a significant role in their deployment strategy. Sarah stresses the importance of balancing security needs with respect for individuals' privacy. John agrees, pointing out that the use of AI for monitoring network traffic must be guided by ethical principles to ensure that it does not infringe on privacy rights or lead to unintended consequences. The team references ethical guidelines and frameworks proposed by organizations like the IEEE and the European Commission to navigate these complex issues. In their final analysis, the team concludes that integrating AI-driven models into their vulnerability management processes offers a sophisticated and proactive approach to enhancing cybersecurity. By leveraging machine learning, natural language processing, and reinforcement learning, they can accurately identify and prioritize vulnerabilities, mitigating threats before they can be exploited. The careful consideration of factors such as data quality, explainability, and ethical implications is essential for the successful deployment of these models. As the threat landscape continues to evolve, AI-driven vulnerability management models will play an increasingly vital role in safeguarding digital assets and ensuring the resilience of cyber infrastructures.